Binary search trees. The binary search trees were briefly introduced earlier. Each node of a BST contains a distinct data item which identifies the contents of the node. The data item is commonly referred to as node key. In a search tree, the keys of all nodes in the left subtree are smaller than the keys of all nodes in the right subtree. In practice, nodes of a tree can contain simple data type such as numbers, characters, or strings. Figure shows some examples of binary trees containing numbers and characters. In many practical problems, such as databases, the nodes of a tree consist of records comprising several fields. One of the fields is designated as record key or key for the node storing the record. Figure depicts an example of search tree which stores personal records. In this example, personal identification number is the node key. Other fields are name and salary. We emphasize that a given set of data item can be arranged in a binary search tree in several ways. Figure shows how the set of characters A, B, C, D, E, F, G can be represented in binary search tree with different tree structures. Notice that two of the structures are skewed to left or right. In these cases, the binary tree actually degenerates into a linked list. Later on, we shall see that the overall tree structure is determined by the order in which nodes are inserted into the tree. Operation on binary search trees. We can specify operations to create, manipulate, and visit nodes of a binary tree. The traversal methods considered in the previous sections are also applicable to binary search trees. In addition to the basic operations for a search tree, it includes create, destroy, and isEmpty methods. Inserting a node into binary search trees. In order to insert, we have to take two things into consideration. First, we need to find a location in the tree structure where a new node can be placed. To maintain the binary property of the tree, the new node must always be added as leaf node. Second, after insertion, we must ensure that binary search property is maintained. This implies that key of each node must remain greater than all keys in the left subtree and less than all keys in the right subtree. Example. Consider, for example, a binary search tree shown in figure. To insert a new node, say Q, we proceed as follows. Beginning with the root, we compare Q with the keys of a node. First of all, Q is compared to S. Since it is less than S, we move to the left child which contains H. We compare Q and H. Since Q is greater than H, we descend to the right child which is G. Again, Q is compared with G. Since it is greater than G and G have no children, we attach Q to G as its right child. Notice that after insertion of Q, the binary search property is preserved. Implementation of insertion procedure. A node can be inserted into a binary search tree by using an iterative or recursive procedure. The iterative procedure uses a loop to perform comparison of keys with the keys of left or right children until a leaf node is reached. If the keys are equal, the loop is terminated with some prompting message. In order to develop the code for insertion operation, we assume that each node of a binary tree stores a character string of some fixed size. The structure of node class is shown in figure. T-node class contains node data. It contains pointer to left child. It also contains pointer to right child. The complete code for iterative insertion procedure is given in reference notes. Searching a binary tree. Searching operation is performed to determine whether or not a node exists in a tree with the given key value. If search is successful, some kind of further operation is performed on the searched node, such as printing or updating the node contents. The algorithm for the search operation is similar to one for insertion operation. The search can be carried out interactively or recursive way. In either case, we start with root node. If the search key matches with the key of root node, the search process is terminated. Otherwise, we proceed to search the left or right subtree according to the key is less than or greater than the node key. If at any stage the key matches with the key of some node, the search process is terminated. If the leaf node is reached and no matches occur, the search process is terminated as being unsuccessful. Example. Consider, for example, a binary tree shown in figure. Suppose we want to know if a node with key values q exists in the tree. We start with the root node and compare q to key value s. Since q is less than s, we proceed to the left child which has key n. Since q is greater than n, we move to the right child which has key m. Since q is greater than m, we descend to the right child which has the matching key. The search is finished. Next, suppose we look for a node with key k. The search path is shown in figure. In this case, the search is not successful because after traversing n, h and j, we end up with a leaf node whose key j does not match with the described key k. Sometimes we are interested in finding the largest and the smallest key stored in a tree. The search for these keys can be performed easily. To find the minimum key, we start with root node and proceed along the extreme left path until we reach the leaf node which would contain the lowest key. Likewise, to find the maximum key, we proceed, beginning with root, along the rightmost path until we reach a leaf node which would contain the maximum key. Implementation of search operation. As pointed out earlier, a binary search tree can be searched by using either iterative or recursive procedure. The iterative procedure is intuitively more clear because it reflects the searching steps as we descend the tree. A code fragment for search operation is given in reference notes. Performance of search operation. We have seen that in performing search on a binary tree, we descend from one level to next level. Further, at each level, we process exactly one node to match keys. In best case scenario, the search value would be found in the root node. In the worst case, the search process would be continued down to the bottom node. Thus, we conclude that maximum search time in worst case is proportional to the height of a binary tree. In our earlier discussion, we demonstrated that the height h of binary tree is given in terms of number n of tree nodes by the formula. Since runtime for search function is proportional to height, we can say that in big O notation, the time efficiency is O log n plus 1 minus 1. Recall that according to big O rules, the additive constant can be ignored in runtime expressions. We therefore conclude that in worst case, the performance of binary search tree operation is O log n. The binary search method is far more efficient than other search methods normally used with arrays or linked lists. For example, with an array containing 1 million unordered data items, we may have to perform on average 500,000 comparisons. If the same data is organized into a binary search tree, the number of comparisons would be around 20. However, for maximum performance, it must be ensured that in building a tree structure, the height of tree is kept to barest minimum. If, for some reasons, the trees become unbalanced and skewed to left or right, then it would degenerate into the linked list with height equal to the number of nodes. In this case, the performance of search operation would be O of n. Traversing binary search trees. The basic traversal operations, in-order, pre-order, and post-order, can be used to process the nodes of a binary search tree. However, we are particularly interested in the in-order traversal because it produces sorted list of node keys. Figure shows the in-order traversal path of a sample binary search tree and the result of traversal. Notice that the visited nodes have keys in ascending order. Performance of tree traversals. In traversing a tree, each node is visited exactly once. Thus, if there are n nodes in the tree, then traversal time would be proportional to n. In addition, some time it would be needed to process the contents of each node. As a result, total time of tree traversal and visit is proportional to n plus c, where c is a constant. We conclude that efficiency of tree traversal is O n plus c or O n, ignoring constant c.